Today, we're going to do something really cool. We're going deep inside a computer program. We're not just going to run it, we're going to crack it wide open and see exactly what makes it tick.
You know, you click an icon, you type a command in the terminal, and things just happen. It feels like a black box, right? Some kind of digital magic that just works. But what if I told you it's not magic at all?
That's right. The files we run are actually built on a highly organized blueprint. And it's a blueprint that we can learn to read, to understand, and as we're about to see, we can even modify it to change a program's behavior entirely.
Okay, so to kick off our investigation, we need a piece of evidence. And we're not going to start with some crazy complex piece of software. Nope. We're going to start with something very, very simple.
Yeah, the classic first program every developer writes. All it does is print "Hello World" to the screen. But trust me, inside this humble little file is everything we need to understand the fundamental structure of pretty much any program on a Unix-like system. So, what is this blueprint I'm talking about? Well, on most systems you're probably using, like Linux, it's a standard called ELF. You can think of it like the architectural drawings for a building. It tells the operating system exactly how to construct and run the program in memory. ELF stands for Executable and Linkable Format. It's this standardized structure that lets a program compiled on one Linux machine run reliably on another. It's really just the common language spoken between the developer's tools and the operating system itself. Now here's a really crucial concept. An ELF file is designed to be looked at in two totally different ways. First, you've got the program header. That's the how to run view for the operating system. It groups things into what are called segments, which are just chunks of the file that get loaded right into memory. But then you've got the section header. That's the what's inside view for tools and developers, and it organizes the file into logical sections. And here are some of the most important sections. The text section? That's the actual code, the program's logic. Our hello world string lives in .rota, that's for read-only data. Then you have .data and .bs for other variables. It's a really organized system, and this separation of code from data, well, that's a fundamental concept in modern computer security. So how do we actually look at all this stuff? Well, we have our own forensic toolkit for this. And two of the most powerful command line tools in our kit are readelf and objdump. Let's start with readelf. This command is fantastic for getting that high-level overview. We can use it to list all the symbols in the binary. Just think of symbols as labels for functions or variables. They're basically a table of contents for the code. And when we run this on our Hello World file, we find some really interesting stuff. We see main, which is where our C++ code starts, but we also see _start. That's the actual first entry point the system calls, even before main. Oh, and check out puts. The compiler was smart enough to use the simpler function to print our string. These are the kinds of little details you can uncover. Okay, time to pull out the magnifying glass. If readelf gave us the table of contents, objdump lets us read the actual chapters. We can use it to dump the raw contents of any section we want to take a closer look at. So, our theory is that the hello world string is living in that read-only row data section. So if we use objdump to peek inside, yup, there it is, the actual ASCII characters for hello world. See? The black box is already starting to look a lot more transparent. We found the data, but what about the code, the actual instructions? Well, we can use objdump for that too. This is where we go a level deeper and ask it to disassemble the text section. It translates the raw machine code, the ones and zeros the CPU actually runs, into a human-readable format called assembly language. Now, quick heads up, when you first do this, you might see something that looks like this AT&T syntax on the left. Notice how it lists the source before the destination. It works, but most reverse engineers prefer the Intel syntax on the right. It puts the destination first, so move EX5 just reads a little more naturally, like move 5 into the EX register. It's just a bit more intuitive to read, so for the rest of this, we're going to tell our tools to use Intel syntax. It makes following a program's logic way, way easier. Okay, we've read the blueprint, we've identified the parts, we've even translated the instructions. Now for the really fun part. We're going to shift from being digital detectives to, well, something a little more hands-on. We're going to rewrite the binary itself. Here's our target. We've got a simple program that just calls the system function to run the clear command. Our mission is to modify this binary so that instead of running clear, it runs shesh, which will spawn a brand new command shell. This is a classic, fundamental technique in security. And the plan is surprisingly straightforward. We're not recompiling anything. We're performing direct surgery on the finished binary. We're going to open it in what's called a hex editor, find the string clear, and just overwrite it with the string sh. This is what the operation looks like at the lowest level. The before line shows the hexadecimal values for the letters in clear. We replace those 5 bytes with the after line. The first 2 bytes, 73 and 68, are the hex for shoe. Then we just pad the rest with null bytes, the 00s, to make sure we fill the exact same amount of space.
And that's it. We save the file, run the exact same program as before, and instead of clearing the screen, a new command prompt pops up. We have successfully hijacked its execution flow just by changing a few bytes of data.
So let's recap our little investigation here. We've confirmed that executables are not magic black boxes. They have a clear, predictable structure called ELF. We used standard, everyday tools to inspect that structure, from the high-level symbols all the way down to the raw assembly code. And most importantly, we proved that by directly manipulating the data inside that structure, we can fundamentally change what a program does. Look, understanding this is absolutely crucial for cybersecurity defense and for malware analysis. Seeing how a malicious program works is the first step to stopping it. But as we just demonstrated, this knowledge is a double-edged sword. It is the very same skill set used to create the exploits that defenders are trying to stop in the first place. What you do with this knowledge, well, that's up to you.